I will talk about galaxies hosting gamma ray bursts. And this is a typical event. This is the gamma ray burst. This is the galaxy, stars on the, along the line of sight. And it's a redshift 0.4. So it's quite typical. And what you observe is that these galaxies are typically small, similar to the Large Magellanic Cloud. They have a relatively high star formation rate, as you would expect. And the growth time scale, which is the stellar mass divided by the star formation rate, which will tell you more or less how long it takes to form the galaxy, is a few gigayears. So it's active star formation going on here. And if you assume that the star formation has been constant for its entire life, you build the stellar mass that you observe in 2 gigayears. So the formation will be a redshift 0.8. Now you have seen, you're convinced that the gamma ray bursts are normally associated with supernova core collapse type 1c. So this is the first supernova detected and associated with the gamma ray burst, and there are no features, and it's a bright event. And a few years ago, Fruchter and collaborators have investigated what kind of galaxies they would host GRBs and these supernova explosions. And this was possible for GRBs are relatively low redshift, below 1.2. And he made a comparison with host galaxies of normal core collapse supernovae. So these are typically type 2 supernovae, not type 1. And he and others have studied where these events occur in the galaxies. And they've shown that typically, typically supernova type 2 are distributed in relatively bright regions in the galaxy, but gamma ray bursts are distributed in the most bright regions in galaxies. So, so you see here that normally supernova type 2, normal supernova would occur in normal big galaxies. Well, these big galaxies are kind of rare, actually, while GRBs occur inside irregular, small, star-forming galaxies. And this is shown here in this distribution of cumulative distribution of GRBs compared to the supernova type 2. So GRBs are most bright regions. So here you have to consider that these are just supernova type 2. If you do the same for supernova type 1c, then where supernova type 1c are distributed, it's more similar to gamma ray bursts. So bottom line, I'm not a supernova person, but I like to show this. GRBs occur in, I mean, they are detected. I mean, the supernova connection is supernova 1c or b. And these are the most massive stellar explosions in the universe. And they occur in very massive objects. While supernova type 2, they are much more common events. And they can occur also in kind of evolved galaxies. You're asking, well, what kind of galaxies are hosting gamma ray bursts? Are spatial in any ways? So you can do many things. You can study metallicity, you can study stellar mass, you can study gas content, dust. And for instance, if you study the galaxy stellar mass versus metallicity versus galaxy stellar mass, and you compare with normal galaxies, you see in normal galaxies that there's a relation, which is called mass metallicity relation. It tells you that more massive galaxies are also more meta-rich. And this relation is observed in the local universe, but also at high redshift in the recent years. I'm sorry, I'm missing the reference here. This is Levesque et al. 2010. Is it possible to make it to shrink a little bit the display? I guess not. So you can study this also with gamma ray burst host galaxies, and it's not particularly easy because the sample is not very large. But it's been done recently by Emily Levesque in 2010, and collaborators, they observed that there is a relation at low redshift and at high redshift, but it's shifted with respect to normal galaxies. So it looks at this relation is there, but it tells you that galaxies with the same stellar mass are more metal poor than normal galaxies. So why is that? Another thing that we know is that host galaxies are normally star-forming galaxies. This is this relation here, the stellar mass versus star formation rate, which tells you how long it takes for a galaxy to build the stellar mass as a function of redshift. And the colored points are GRB host galaxies. The stellar mass star formation rate is proportional to the size. The stellar mass is proportional to the size of the symbol. And it tells you that this is the age of the universe. It tells you that most of these galaxies are active. They're young objects. And this is the crosses are and the points are comparison with normal galaxies. If you want to know what short GRBs are, these are the red circles here. So they're distributed, but it's hard to tell because the sample is very small. So what do we know from this sample? If you took, what we know is mainly a low redshift sample, redshift lower than 1.5. So GRB hosts are generally small, are metal poor, not much dust apparently, and they start forming. And so we want to know, is this typical for the entire universe, for the population of galaxies, and is it actually changing with redshift? So what happens at higher redshift? The problem is that it's difficult to detect these galaxies because normally they're very faint, but we start to have some ideas. And when you want to learn this, you have to consider that the universe had some major changes from redshift 2 to now, to redshift 0. And the changes are about star formation rate, stellar mass, galaxy merger rate, and also galaxy size. So we are talking about the general population here, and these are the changes that happen in the universe in the last 8 gigayears or so. Yes? Dust extinction is not very high.
As an infrared source, they're not powerful, but there are plenty of red and
yes, I agree with you. But if you talk about people looking at gamma burst host galaxies, they will tell you that there's dust poor. That's the common belief. But I agree that there's a lot with, and I will show something about this, and I will discuss this. So about the size at high redshift, they can be very small. So that's why there is one reason why it's hard to study them. If you take Andromeda and you shift Andromeda to redshift about 2 or so, it will be much larger than a GRB host galaxy. But the universe itself is changing from redshift 2 to, this is this plot will show you how much the half-light radius is changing in galaxies from redshift 8 to 2. So these are normal galaxies. These are the bright ones, these are the faint ones, and the change in the size is dramatic from redshift 8 to 2. And it's changing also up to the local universe. So the fact that they are small galaxies is not surprising.
Do you have similar plot for how the metallicity is changing with redshift? To see, for instance, that redshift you are finding for GRB host galaxy is smaller compared with solar metallicity. And so the sense of the question is whether that smaller metallicity is something peculiar and particular to GRB host galaxies, or is that typical of the redshift interval at which GRBs are seen?
The answer to this is it's a total mess, and I'll show you. It's a total mess. We cannot Well, people say they're metal poor, but not always. And actually, some GRBs have high metallicity at high redshift. So this I will show you in a moment. So I'll be able to confuse your ideas a lot.
I was hoping for some clarification. I'm already very confused.
Okay.
So,
Yeah, I think there is a lot to learn.
yeah, so that one is covered, really.
So I'll show you a few facts about the evolution of the universe in general for galaxies, for normal galaxies, not for GRB host galaxies. So what we know is that the star formation rate density of the universe is evolving, and also the major merger rate. And the change is dramatic from redshift 1.8 to 0. It's a factor of 50 in star formation rate density in the universe. So in the past, there were 50 times more star formation rate than in the local universe. And the major rate between big galaxies has also changed by a large factor from back then to now. So we would imagine that this would have an effect on the nature of GRB host galaxies, because GRB is a phenomenon associated with massive stellar explosion and also massive star formation. Okay. And
you're assuming the star formation rate is dominated by the massive stars.
Well, this it's an indication that there is a lot of star formation if you have massive stellar
So
explosion.
you're assuming the mass distribution is changing, right?
Say that again. If
You're
you're
assuming the mass distribution of the stars, right?
Uh-huh.
So when you form stars, you get a mass distribution,
Uh-huh.
some kind of a power law or something.
Yeah, I don't assume anything. These are just galaxies. You observe the star formation rate in galaxies, and you measure the star formation density in a volume, and you see how this changes with time. I don't see anything about the local, where the star formation is actually happening, and if galaxies have a different IMF, the initial mass function, or something. This, I don't do this. What I can tell you is that this is the same plot in different paper. Where you see here is the star formation rate density done for different stellar masses. So these are the massive galaxies. These are less massive galaxies. And what you see here is a drop of contribution from massive galaxies in the star formation rate density. So big galaxies were contributing, but after redshift 2 or so, they were not contributing that much in the star formation rate density, in the history of star formation rate density. So if this is true, you might imagine that a low redshift star formation rate happened generally in small galaxies. And you would conclude that you would expect gamma ray bursts to occur in small galaxies. So all this looks kind of normal in the end. So you would expect at redshift below 1.5 that GRBs happened in small galaxies, because contribution from big galaxies is relatively small. About the metallicity, the mass metallicity relation here in the local universe, it looks like this. There is a large dispersion. But recently, Manucci et al. And others also have demonstrated that this mass metallicity relation is also a function of the star formation rate. That means that if you have a metal poor galaxy here, if you have a galaxy with large star formation rate here, you would expect to be more metal poor for the same stellar mass. Is that clear? No. Okay, so one step forward.
It's on the slide, everything is backwards.
So that is exactly, totally counterintuitive. Please say it again.
Okay.
So that I want to make sure that I didn't mishear you.
Okay. So this is the mass metallicity rate. Now you add another parameter, and you put star formation rate in the galaxies. And this is what you get. So for higher star formation rate, your metallicity is lower.
That's,
Yeah, it doesn't make sense.
that makes very little sense, really.
Why not?
Could you
Why?
physically, I mean, if you have a higher star formation rate,
Yes.
right, assuming that the IMF, the initial mass function, is not metallicity dependent, assuming that, then you would expect that higher star formation means that you would have a fraction of a star, higher rate of
Metal
massive
product.
star form, which
Yes.
would then explode and enrich the galaxy with more metals.
Yeah, but it also tells you that the galaxy is young, has a lot of gas, and maybe didn't have the time to pollute the gas with metals.
It's still higher. I mean, that is reflected in your x-axis, no? X-axis is showing what the mass is.
But this is it's the stellar
I know
mass.
that.
It doesn't tell you how much gas there is.
True, that's true. But
It would be interesting to see if there is also another parameter, which is the gas fraction. If your gas fraction is lower when the star formation rate is high, then you imagine this galaxy to be metal poor. It's in the process of forming and to enrich the gas with metals.
there's another effect that I could kind of understand, that it will push things in the direction that you are projecting, or the observations are. And that is that the smaller a galaxy is, the smaller is the gravitational potential.
Yes.
And when a star explodes, then
Yes.
the metals, meaning the remnant, is not bound to the galaxy and escapes.
Yeah.
And that is something that I can kind of understand.
Yeah,
But
this
that
is what Manucci et al. Actually are concluding, that the
Sorry,
wind,
sorry?
Manucci et al., the people actually found this,
That is what they are
it's called
concluding.
fundamental, yeah, they assume that there's strong wind in the galaxy and the metals will be ejected in the intergalactic medium. This is what they conclude. But they don't say anything about what's the total mass of the galaxy. It might be that those galaxies with high star formation rate, they have a lot of gas, where metallicity is low because there's a lot. It's young, it's still star forming. So it's debated at the moment. Something new, 2010.
Can it be also interpreted as merging or reducing higher mass of galaxy is accompanied by nuclear synthesis?
Merging,
Yeah.
the merger of galaxies.
And formation of much more bigger galaxies is accompanied by nuclear synthesis. Is it true?
I don't know. I think we're still debating. We're still debating whether mergers is actually common in gamma-ray burst host
How to
galaxies.
reduce higher mass galaxy?
Star formation, yes. Merging, yeah, but I mean, the merging is actually boosting the star formation rate or quenching star formation rate, because this is also not clear. So the other thing is that the mass metallicity relation is evolving with redshift in this way. Okay, so you have to consider the relation, but also that it's evolving with redshift. Okay. Another thing that we need to consider is the cosmic stellar mass assembly. This plot shows how many stars there are in the universe as a function of time. And in the recent time, let's say in the recent 8 gigayears, the stellar mass of the universe doubled, more or less, which is not a large increase in terms of stellar mass. So that tells you basically that there's a major change for redshift higher than 1.2, but after redshift 1.2, then you expect gamma bursts to occur where star formation rate happens, and star formation rate happens in small galaxies.
But wouldn't this argument speak against the previous interpretation of the unknown gas mass? Because the stellar mass only doubles, the
Yes.
gas mass cannot have such a big effect.
Yes. It's a multiple dimensional universe. It's much more confusing than it looked before. Before it looked so much easier. Metallicity was low at high redshift, now it's high. But now it's not clear. Yes.
Can we, for just a second, go back to the previous slide?
This
yes,
one.
and the one next to it, which is to say, no, not next to it. Meaning then you had put this effect of star formation rate. Great. So now, in the view of this particular information, we go back to the claim that metallicity for GRB ghost galaxies is lower but they are also smaller galaxies, meaning maybe 1/10 of the L star galaxy, right? So now combining this graph and asking the question, is the metallicity of GRP host galaxies really smaller compared to what you expect for 10% L star galaxies? What's the answer?
Yes, exactly. Maybe not. Maybe it's normal.
But I'm asking you, I mean, that's a no,
Yeah.
right?
Well, I mean,
Is-
now,
is not-
yes, I agree. I mean, to me, GRB host galaxies, there is no evidence that they are spatial galaxies. They look spatial because they are actually detected with gamma ray detectors. They don't select galaxies according to brightness or how much star formation rate there is, or if you have strong metal lines. They're just detected because there is a gamma ray explosion there. And in principle, it's a random selection of galaxies. Just you have a very rare event that is the explosion of a very massive star.
I mean, that is the question, right? Whether it is a random selection. I don't want to dwell on it for too long because I know you have many other things to cover. But I just want to clarify this particular point, whether GRB host galaxies are special, but only in the sense of metallicity. Because there are a number of claims, number of papers claiming that the metallicity is small. And
I'll show you.
The question is whether it is small compared to the size of the galaxy.
No, I think a low redshift, you expect this to be low generally, but high redshift things can be different. And there's a large spread of metallicity in the host. And it's very hard to convince people otherwise because they've been talking about metal poor because the progenitor has to be metal poor, because you need to have a zero metallicity star, otherwise you lose winds and you lose angular momentum. That's the main problem. But it is not fully demonstrated that this is the case. I mean, they're associated with supernova type 1c, which they lost a big envelope, big, fraction of the mass. So, anyway, maybe I should skip something. I just wanted to show this that Anatoly showed yesterday. These are spectroscopically confirmed objects. So the record for quasars and galaxies and GRBs are way above galaxies and quasars. And the advantage of using GRBs as a, to detect high redshift objects is that they disappear. And when they disappear, it's an explosive event, like in this case. The redshift is not particularly well determined, but it's at high redshift. And when you have a galaxy like this one, I don't know if you remember this, was published a few years ago. It's not this paper here, I think it was 1 or 2 years before, that they claimed that this galaxy was a high redshift galaxy, at redshift 6.2. At that point, it was a record for galaxies. And when you have photometry and photo Z for galaxies, you cannot be sure that this is a high redshift object because you always have a competition with possible, without this other minimum in the chi-square distribution for redshift, which is a redshift about 2. So you can have a small galaxy, red because there is dust, or there is metals, there's a lot of metals, and you can still reproduce this distribution of points in the SED. And actually this object it's in the HUD, Hubble Ultra Deep Field, and it was reanalyzed again by these people here. The original paper, I don't have the reference here. And with the same data, they found that actually it was very likely a galaxy at redshift 2.6. So when you have GRBs, it's easier because you know that it's a power law, that it's disappearing, so it's easier to get the photometric redshift. So the problem with gamma ray bursts is that they fade quickly, but it's also an advantage because once it's gone, it is easier to observe the galaxy itself, regardless how bright it is. So it is the GRB is brighter than the entire galaxy for a moment, but then after a few weeks, it's gone, so you can look at the galaxy itself and learn a lot of things. And a high redshift, this was done using quasars like a background point source that would illuminate the galaxy and tell you a lot of information about the interstellar medium galaxies at high redshift. With GRBs, you have the GRBs itself in the galaxy, and you can do similar things. You have the spectrum of the afterglow, and you have lots of information coming from the interstellar medium, which is absorbing the emission from the GRB, and you get a lot of information about the gas. And once it is gone, you observe the entire galaxy, you learn more about the host galaxy, the hot phase of the gas, for instance, with the emission lines, and also doing photometry, you learn something about the stellar mass, star formation rate, and the history of the galaxy. So there is a lot of information there. The trouble is that sometimes to combine everything together is difficult. So to give you an idea, if you use a quasar as a background source, quasars are very bright. And they shine for a long time, so they don't disappear like gamma bursts. So this is how we study the metallicity in galaxies at high redshift for a long time. And then people started to look at galaxies themselves. So imagine, this is quasar, which is 70 magnitude, and here you have galaxies also at high redshift. They are much fainter. But you can do, what you do is you study the emission, not the absorption of the galaxies. And they're still relatively faint. When you have a GRB, the GRB doesn't care how bright the galaxy is, and you can end up studying very faint objects. Okay, and this is kind of difficult. And because emission lines are in the optical, and they are studied in the optical up to redshift 1, 1.5, and absorption lines are UV lines, and they are detected in the optical for redshift larger than 2, generally speaking. The two samples are kind of disconnected. So here you study the GRB host itself, and here you study the GRB DLA, this large absorption, which means damp Raman alpha absorption. And it's UV lines associated with the cold interstellar medium. So I showed this comparison between the histogram of GRBs as a function of redshift with comparison with quasars, just to show that it's much flatter in terms of time. This is log of time, or 1 plus z. And I like this better than using just redshift because it stretches time for low redshift, for the low redshift universe. And if you compare this with the star formation rate density of the universe, it doesn't look terribly different. That means that probably we're not missing many objects at low redshift. So I showed this for you because you had this plot yesterday, star formation rate density compared to gamma ray burst histogram. And you said that the GRBs are many more than what you would expect from star formation rate density studied normally with normal galaxies. But from here, it's not clear whether you're missing anything or not. So it is a powerful way to actually study the evolution of star formation rate density in the universe. And this was done in the last few years by many people. This is the star formation rate density again, the same as I showed you before, but with the real points. And recently with gamma ray burst, this is how it looks like, and the normalization is kind of difficult. It was done again by others, and it looks different. The normalization is done here this time. And it might be that, as we said yesterday, that GRBs are basically telling you that the star formation rate at high redshift is much higher than what it is observed from normal galaxies. So it might be that we are missing a lot of action here. And gamma bursts will tell you something. If you want to know what happens to massive galaxies, so these are sub-millimeter galaxies here, the star formation rate given by sub-millimeter galaxies, massive galaxies, a lot of dust, a lot of large objects, large stellar mass, and the star formation rate is 20% given by these galaxies. And it goes up with redshift, so it might be also with these are ultraluminous infrared galaxies, it might be that if you go even higher redshift, the contribution to the star formation rate density might be more important than what it is at redshifts lower than 2.5. About metallicity, so this is for you. These are two different afterglow spectra, one at redshift 3.6 and one at redshift 2.1. And I think I had some, maybe I lost something, but here the H1 Coulomb density is about 10 times lower than here. So this tells you how much gas there is in the galaxy. And the metal lines here are much stronger than here. So the enrichment in metals in the host galaxy is much higher in this object than it is here. So that tells you that the fact that these objects are always metal poor is not totally right. Certainly not at high redshift. So is this confusing enough? Yes. So I'll show you more points in a moment. So this is the same object here, metal rich, and I compare this with the metal poor galaxy in the local universe. And so this is dwarf galaxy at redshift 0.01. And you see here, H1 is much more. Metal lines, I mean, I'm comparing with the same wavelength. Metal lines here are much weaker than here. And this might be a typical host galaxy for a gamma burst or low redshift, but here it looks totally different. And the other thing that you might notice that often people say fine structure lines in GRB host galaxies are indicating that there is a gamma ray burst there, because it's an excited gas and it's coming from the UV light produced during the explosion. But silicon, for instance, silicon 2 star here and here is also observed in local dwarf galaxies. So the presence of fine structure lines in galaxies doesn't indicate the presence of a gamma ray burst also. The gamma ray burst, not necessarily. So here, if you compare these galaxies, those three that I show you, here's the local dwarf galaxy, here's the low redshift object, 980425, the one with the supernova, and this is the high redshift one. You see that these three objects, these three galaxies have nothing in common one with the other. Not the stellar mass, not the star formation rate, not the metallicity. So we don't have a typical host galaxy. The only thing that we know is that the host galaxy has to be star forming. We're talking about long gamma ray bursts. So this is the metallicity plot that we have been knowing for a number of years for the universe. Metallicity is a function of redshift and measured using quasars as a background light. And the quasar is a random object. It's crossing galaxies, the light, and then you can study the metallicity for many, many objects. We have hundreds of objects right now. And you see that there is an evolution with redshift, which is very steep. 10 minutes. 1 second, I want to see where I am in my plot. Okay. And if you add what we know for gamma ray burst host galaxies, first I'll show you this. So this is what you would expect given the mass metallicity relation. And it's also predicted by models producing metallicity evolution given the star formation rate density. So you would expect an evolution with metallicity which is much flatter, and it also depends on the stellar mass of the galaxy. So it's steeper for objects that are smaller, and it's flatter for more massive objects. So this is this evolution with redshift that you find with quasars would tell you that there is a metallicity crisis. And this was known for a number of years as the missing metals problem. So models would predict more metals than what we actually would see. Gamma ray bursts you have, and At low redshift, you measure metallicity from emission lines, and they are relatively low, generally speaking. If you use absorption lines, then you have the same situation with quasar. You have an object at high redshift explosion, and the absorption lines and the metallicities are spread all over. There are some that are metal rich, some that are metal poor, and this object here is the one with high metallicity. And the spread in metallicity is over 2 orders of magnitude. And recently, there have been 2 galaxies studied with emission lines that show high metallicity. So this will make the picture more confusing also for the low redshift universe. So the situation is a total mess. The metallicity evolution of the universe is a function of how large the galaxy is. And since there is a large spread in the universe, you can expect anything. So about the mergers, would you expect these objects to explode in systems that are merging? We have some evidence that this can happen, not so rarely. The metal-rich object that I showed you show very strong metal lines separated by 2 systems separated by 700 kilometers per second. And it's not unique, there are others. And this is another one. And the separation here is also similar, 700 kilometers per second. And another one, this is a little larger, 2,000 kilometers per second. So the fraction of these double absorbers at high redshift associated with the GRB afterglow is relatively high. A factor of a few higher than what you would expect using absorption lines in quasars, the quasar as a background light. And what do we actually see? Here are other targets. It's also high redshift, 2.6. We have the GRB happening where the arrow is pointing, and you have 2 objects here. This is the afterglow spectrum here. So the H1 absorption here and lots of metals. And then you can observe A and B, and you see the spectrum here with emission lines. They are at the same redshift of the GRB afterglow here in the middle. And the separation here is could be about 20 kiloparsec or so. So they are interacting systems, and the separation is large, but not terribly large. These are parameters for the host galaxy. It's relatively, well, the stellar mass is not well determined. H1 is very high. Metallicity is kind of low, but this is expected for high redshift. Star formation rate is not particularly high. This is another system. Forget about this yellow line. The host is here. The host was observed recently. These are the parameter for the host galaxy. It's a massive galaxy. Its star formation rate is very high. And the galaxy A, which is separated by, I would say, about 20 kiloparsec, well, 15, 20, is at the same redshift of the host galaxy. So here's the spectrum, the host here, and the galaxy A here. So the separation is kind of large. But again, if you compare this with the Andromeda galaxy at the same scale, these 2 blobs can belong to the same system. They are could be gravitationally bound. Another example is here. Yes?
Sorry, could you go back to that spectrum? I'm sorry, I can't see the velocity. Is that a fat line?
Do you mean this one here?
Yes.
This is 500.
So those lines are...
No, wait a second, I can see.
Or 200 okay.
Yeah, they're large, yeah.
So it's not unusual.
Huh?
It's not
You mean if it's an AGN? Well, it is large, yeah. But I think they are supposed to be larger at high redshift because the these are compact objects and massive. The mass is similar to the Milky Way, but very compact, and you would expect the velocity dispersion to be larger, the rotation to be larger, otherwise gravitation will dominate and the galaxy will collapse. So I believe it is expected to be a little larger than what you would typically see in the local universe.
So there is weak AGN activity?
In this case, I don't know. AGN, people have been looking for AGN contamination in these host galaxies, and it was not found. Normally, it's not found. Maybe there is one K.
But the oxygen 3 is not narrow, which is weird for AGN. So I don't know.
I understand.
Okay, sorry.
Yeah. Well, yes. I can have a look and see better. But yeah, it's a good point. Yeah, it looks, it also gives a better impression because this is high resolution. So you wouldn't expect to have such a big thing at redshift 2.3, but it's high resolution, so it looks larger than what you normally see. And it looks in the sense that normally you cannot have resolved emission lines because normally you only use a medium resolution spectroscopy. I have to continue, I'm afraid, but we can talk more about this. This is another case. Also here, companion and a double absorber here, and the emission here. And very, very recently, like a couple of months ago, this galaxy here, at redshift point 28, had an explosion, and the separation from the host galaxy is 8 kiloparsec. How many minutes? 2 minutes. This one, do you remember? It's a supernova. No, I think the supernova was detected. It's the very recent one. It's a long, I guess it's long. I don't know the duration. Yeah, but the supernova was seen. So the other question is, what's the relation with massive galaxies at higher redshift that have massive star formation rate and massive content of gas and dust? So this is a nice picture of a star forming region in the Milky Way, in the optical and in the infrared. I mean, you see much more when you go high with high wavelength. And so going back to your question about AV, it was recently found that the afterglows of GRBs can have very high extinction. If you are fast enough that you can actually detect the afterglow early on, and regardless how much dust there is, you can see them. So if you can do this, there is a fraction of these GRB afterglows that have high extinction. And the trouble is, when you have high extinction, then it is very complicated to do anything because the objects get very faint. So when they're faint, you don't see them. What you see is what is here when AV is very low, and then you conclude there is no dust. But it's not true. Dust can be large. And these objects can be also at high redshift. The difference is that you have to be really fast.
But that's a small fraction with large extinction.
There's a small fraction with large extinction, yes. But we don't know whether we are missing something up here. Yeah. And if you want to see the stellar mass, I mean, these are normal galaxies at a low redshift here, the dark points, and the red points are the high redshift, or redshift 1. And if you want to see what's the stellar mass of host galaxies for a small sample, a low redshift, below 1.6, we still don't know whether, I mean, the error bars here are very large, but it looks like there is a contribution from massive galaxies. Do I have a minute? No minute. Then I'll show you the last slide, which is this one here. We had some hope that maybe some of these host galaxies will be sub-millimeter galaxies, but a few weeks ago, this paper was published was an astral pH. And this shows you that some of these objects have high submillimeter emission, which would indicate lots of dust and lots of gas and lots of star formation. But with more observations at high redshift, lots of these host galaxies are showing just upper limits. There is no radio submillimeter emission in these objects. And so they would be probably more comparable to normal Lyman-Break galaxies at high redshift here. So this is the GB host population and the comparison with submillimeter galaxies. They are kind of different. So the last one is my conclusions. GB host galaxies are important probe of galaxy formation and evolution. There is a fraction of them that are dusty, but detected finally if you are fast enough. And the chemical evolution is spread over orders of magnitude. There is no chemical evolution, not detected so easily. And star formation rate density can be probed using gamma ray bursts. So we rely on SWIFT, and SWIFT has been funded for another 2 years until 2014. And after this, we need to have another mission ready, or maybe have more support for SWIFT. Thank you. Sorry for taking so much time.